So this lecture is kind of setting kind of the methodological basis for today and these techniques, and then Donata will talk about some of the sort of the more scientific aspects of this and how some of the choices you make here will, affect the science you do with your interpolated maps. But yeah, so that's more or less the plan for today, and then in the afternoon you'll have an activity to explore these things yourself. So a big motivation for today and for my work in this space, and also kind of a very good case study to keep in mind when we talk about spatial-temporal interpolation of oceanographic data is the Argo array of profiling flows. So I think many of you probably know about this, but in case you don't, so Argo is this a global kind of mission to observe the ocean using flows that go up and down in the ocean. So these are autonomous flows that go up and down in the ocean. They are 2,000 meters, and they measure temperature and salinity. There's about 4,000 of those. This is where they were a couple of days ago. You can see that they cover the globe very nicely. They are roughly speaking unbiased in terms of their sampling, and this data exists since about 2004 or so, more or less. So about 20 years of this data available now. And one of the main reasons this data exists is to measure ocean climate and especially the ocean heat content, which is, Donata will talk about that, and that will be part of the activity in the afternoon. But in order to do that kind of science with this data, one of the things you need to do is to kind of realize that these data are kind of spot observations, but what you usually care about is actually the underlying field. So you need some way of infilling gaps in this array. You need some way to kind of say, okay, what is my best guess of the value of the field here where I didn't actually observe it? Like there you actually have a float. The floats are pretty precise in terms of their sensors. So where you have a float, you more or less know exactly what the value of the field is. But of course, the floats, they cannot cover everywhere, so there will always be gaps, and you need to infill those gaps one way or the other. So the task of doing that is statistically called the spatio-temporal interpolation problem. You want to interpolate these sparse observations over space and time, and that's the topic for today, and especially for this lecture is to learn how to do that. And yeah, so this is the task. So on the left we have the data. This is what is available to us. And what we want is a map like the one here on the right. This is in fact one of the Argo ocean heat content anomalies that we've produced. And the question is, how do we do that? And this is of course a much bigger problem than just Argo. So this applies to almost any in situ observation in oceanography. There's many devices that can produce such observations, the Argo floats, but also moorings, drifters, gliders, ships. There's even one picture of a marine mammal with a sensor. So in all of those cases, you need to one way or the other deal with this problem of, you are usually need to deal with this problem of like going from the sparse observations into a continuously interpolated map over space and time. So we need to solve this spatial-temporal interpolation problem, and the question is, how do we do that? And so really what we want to do is to go from this irregularly spaced data into a regular grid over space and time. So of course this is, it's still on a computer, so it's not really a continuum function. It really, in reality, it's over a grid. So it's over a grid of space and time. And the question is, how do we effectively go from this irregular data to a regular grid over space and time? That's one way to understand what we want to do here. So here we are going to do this through the language of Gaussian processes, or Gaussian process regression. And the reason I do it is, first of all, it's relatively easy to motivate and understand how those things work, but then also that approach will produce the same interpolation techniques that are widely used in oceanography. You might have heard of like objective mapping or optimal interpolation. So these techniques will produce exactly those spatial-temporal interpolants. But I feel compelled to say that there are also other ways to arrive at those same interpolants, and there are also many other interpolants. So this is not the only way to interpolate data over space and time. This is also not the only way to derive these estimators. But I think using Gaussian processes is a helpful way to do this. So that's the perspective I take here. So basically the plan for this lecture is there will be kind of three parts. So I'll first talk about kind of the mechanics of Gaussian processes generally. Not just within spatial-temporal interpolation, more generally. Then in order to work with Gaussian processes, you need to make certain choices about mean functions and covariance function and parameters. So I'll talk about how you do that. And then we'll put these two things together and learn how to use those in the context of oceanographic data. So that's the plan. So before we get into that, I want to set the stage here in terms of, okay, what is the kind of the basic setup? Like, what is the basic principle we are going to follow when we do this kind of statistical interpolation of data? So the basic starting point is that what we basically do here is to regard the spatial field, the underlying spatial field, the physical field, whatever was the true state of the ocean. We are going to think of this as a random realization from some underlying stochastic process. And of course, the real ocean state probably is not really random. It really came from some kind of a physical process, but you know, over a long period of time, you can think of those kind of instantaneous states as coming from some kind of a random process. And if you are willing to make that assumption, then all of these things, all these methods kind of come into picture at that point. So, okay, so there's a couple of terms to define here. So first of all, stochastic process. So what is a stochastic process? So mathematically, a stochastic process is a collection of random variables, something like this, that is indexed by indexed over a continuum. So there's some index into this collection of random variables, and that index is over a continuum. So in this particular case, it would be a real vector over some d-dimensional space. So there's some d-dimensional real index into this collection of random variables. And indeed here, so you think of this as like x is an index, and for each x there's a random variable. So this f of x is a random variable for each x. And as over x, this is a whole big collection of random variables. It's a uncountably infinite collection of random variables. And in fact, I kind of wrote this as f of x on purpose because the alternative perspective of what this is, you can think of this as a random function of this input x. So you can either think of this as a big collection of random variables, or you can think of it as a random function, and those are actually the same thing mathematically. So and now this x it's over a d-dimensional space, so it can be a function of one variable, a function of two variables, three variables, and many other variables if you want. But specifically the first three dimensions, these are relevant for oceanographic data in particular. So if you are in the case of that the input domain is a subset of the real line, and then we often, in that case, think of this x as being time. Then we are talking about temporal processes. On the other hand, if you are in the case that this domain is in a 2D space, then we often think of that as being a process over space. And in this case, the x represents the latitude and longitude coordinates. And then the next kind of higher dimensional version of this is you add time. So yeah, and then now you have a spatio-temporal process. So the input is over a 3D space. And just to give you an idea of what this might look like, so here we're talking about a random function over a 1D space, random function over a 2D space, random function over a 3D space. So what might that look like? So here is an example of what this looks like over a 1D space. So you would think of this as being time here, this x-axis, and then each of these different curves is a random function of time that will be generated by this stochastic process. Or in 2D, you would think of this as being longitude and latitude, and then this would be a potential realization from a 2D random function. And in other words, what we are looking at in here is a spatial field. And you can easily think of some kind of an oceanographic field as looking like something like this. Okay, so this is the basic setup. So this is very important to understand that when we talk about these methods, we always think of the data, the underlying field. So there's no data yet. We're just talking about the underlying field as being for a random function or a stochastic process in other words. Another question is, how do we work with observations from these random functions? So the basic setup is going to be that I get to observe these random functions at certain places over this x domain. And the question is, what do we do with such data? To basically try to guess what the underlying, what the rest of the process might look like. So, So now that we have that out of the way, now what we are going to do is to develop sort of the methodological framework for doing this using a particular type of a stochastic process called a Gaussian process. Yeah, so in order to do that, the very first thing I want to do is to kind of give you a recap of multivariate Gaussian distributions, because it turns out that in order to do things with Gaussian processes, really the only thing you need to know is how to work with multivariate Gaussians. So this is important to kind of remind ourselves about a few things about multivariate Gaussians. So first of all, okay, so what is a multivariate Gaussian random vector? So it's an n-dimensional vector that has a particular distribution. So this is the PDF of that n-dimensional vector, and if it has this PDF, we call this a multivariate Gaussian or an n-variate Gaussian distribution. So if you connect this with the lecture on Monday, this is a particular parametric family of distributions or statistical models. It's parameterized by a mean vector and a covariance matrix. And the particular meaning of these two parameters, so these are now parameters of the statistical model. It's a parametric family of these two things. And what is the particular meaning of those two parameters? So the meaning of this, as you might guess from the names, is that the mean vector is basically characterizing the expectation of each component of this random vector. And then the covariance matrix, it's characterizing the covariance between any two elements in that random vector. And this, the only additional thing you need to know is that this cannot be any matrix. It needs to be a symmetric and positive definite matrix for this covariance to make sense. So that's what a multivariate Gaussian is. Now, multivariate Gaussians are nice because they have a lot of nice properties. So actually, we can do a lot of things in closed form, a lot of operations in closed form with this. And it's important to know this because these are the key operations that make life with Gaussian process easy. So it turns out that more or less you only need to know these things to work with Gaussian processes. So that's why we will go through this in briefly here. So okay, so now take your random vector y and divide it into two components like this. So you put the first few variables in this y1 and then the rest in y2, and then you can similarly divide the mean vector and the covariance matrix in the same pattern. And then you can now ask questions. Okay, so we know that we assume that this y, it has this distribution. So now the question is, what do we know about these individual components? So the first question you might ask is that, okay, so what do I know about the distribution of just this first component here? So what is the distribution of y1? So this is called the marginal distribution of y1. And it turns out that that is also a multivariate Gaussian, and in fact, it's sort of the multivariate Gaussian that you might have guessed if you have not seen this before. So it's a multivariate Gaussian that has the mean being these components from the original mean vector, and then the covariance matrix being this block of the original covariance matrix. So that's nice. So we even know what the marginal distribution of any subset of a big Gaussian random vector, what that marginal distribution would be. But maybe more importantly, what we also know is what is the conditional distribution of this y1 given y2. So what is the so this is basically answering the question like, what do I know about this part if I have seen this part? And it turns out that's also a Gaussian, and it's a Gaussian that has this particle form here that for now it's not like super important what's exactly in here, but basically involves these different components of both the mean and the covariance here. The key point is you can write this down in closed form. It just involves like vectors and matrices here that come from the original mean vector and covariance matrix. So these multivariate Gaussians, they're sort of closed under both marginalization and conditioning, in the sense that if you start from something that's multivariate Gaussian, then the marginal distributions are going to be multivariate Gaussian and the conditional distributions are going to be multivariate Gaussian. And here, it doesn't actually matter what you put in here and what you put in here. So you can always rearrange your original vector so that any components you want are here and then the rest are here. So this means that basically for any subset of variables, you know what their marginal distribution is and what their conditional distribution is. All right. So these two things are, especially this thing is really a key feature of multivariate Gaussian. In fact, this is also key for making inferences with Gaussian processes. So this is really the sort of kind of the real tool that we are going to be using here. All right, so this was the brief reminder of what a multivariate Gaussian is. So now let's try to connect this with this idea of a Gaussian process or a random function. So how do we go from what we just saw into a random function that we call a Gaussian process? So in the previous case, we had a collection of n random variables. So these would be the elements of this vector here. So I'm just listing the different elements here. There's n of them, and what we just discussed is jointly have a multivariate Gaussian distribution. Now imagine that you make this n very large, so that there's a very, very big list of these. Maybe there's 1,000, maybe there's 10,000, maybe there's a million, maybe there's a billion of these. So at some point there's a very, very, very big collection of these. And if you basically take that limit where you make this n infinitely large, so you basically have an infinite collection of these kind of Gaussian random variables, that's what gives you a Gaussian process. That's one way to understand how to get a Gaussian process. Because at that point, basically, this discrete index basically becomes a continuum index. The index set becomes so big that it becomes a continuum. And at that point, and in that limit, that's what we call a Gaussian process. Or the more rigorous definition is down here. So a Gaussian process, so first of all, Gaussian process is a stochastic process, so it's either a random function or it's a continuously indexed collection of random variables, and it's a stochastic process that specifically has this property that so it's a random function that has this property that if you evaluate it at any finite set of locations, so you ask what is the value of this random function at x1, x2, xn for any arbitrary x's, that is a finite collection of them, it has the property that this collection follows a multivariate Gaussian distribution. So that's the definition. A Gaussian process is a random function whose finite evaluations over an arbitrary collection of inputs follows a multivariate Gaussian distribution. So this is nice because it basically means that whatever finite evaluations of this Gaussian process we get, they will follow the multivariate Gaussian distribution, which means that all of this stuff applies. Okay, so here's the definition again. So now this new stochastic process we just defined, it will be parameterized by something. Similar, like exactly the same way as a multivariate Gaussian is parameterized by the mean and the covariance. The question is, what are the things that parameterize a Gaussian process? Well, the answer is that it's sort of the analogs of the mean vector and the covariance matrix. But now, because we have this infinite collection of Gaussian random variables, it's no longer a vector and a matrix. Instead, you get a function, and well, actually you get a univariate function and a bivariate function. So specifically, the analog of a mean vector, in this case, is a mean function, and the analog of a covariance matrix is a covariance function. But those two things are still defined very similarly to what we did in the case of a multivariate Gaussian. So the mean function at x is simply the expectation of this random function at x. And the covariance function is the covariance of the random function at x1 and x2. And these things here, these are defined exactly the way any usual expectation or any usual covariance is defined, because this f of x, this is just a random variable. So you can ask, what is the expectation of this random variable at x? And that's the mean function at x. Similarly, this f at x1 is just some random variable, and f at x2 is just some random variable. So you can ask, what is the covariance of those two random variables? And since they are indexed by x1 and x2, there's a whole collection of those covariances, and this covariance function collects that collection of covariances into a function. So exactly the same way as a multivariate Gaussian is parameterized by the mean vector and the covariance matrix, a Gaussian process is parameterized by these two things. So then we basically use this notation that we say that we get an f that is sampled from a Gaussian process with mean function m of x and covariance function k, x1, x2. Okay, so So similar to what we discussed with the covariance matrix, that not all matrices are valid covariance matrices, the same thing is true for these covariance functions. Not all functions are valid covariance functions. So specifically, what we need to guarantee is that whatever, like, so this covariance function gives us these covariances, which lead to the covariance matrix of any collection of these points. We need to make sure that that covariance matrix is a positive definite matrix. And not all functions give you that. So especially those functions that give you that are called positive definite functions. It's not like super important like how those are actually characterized, but the important thing to keep in mind is that not all Weisbach functions are valid covariance functions. All right, let's proceed. Okay, so now we have the basic definition of the situation. Now we ask the question, okay, how do we work with this Gaussian processes? How do we do statistical inference with these Gaussian processes? Because really what we are trying to do is to solve the spatio-temporal interpolation problem. So the setting here is that we are going to assume that our oceanographic data are a Gaussian process. So that field we see, we think of that as coming from a Gaussian process. And really what we are trying to do here, we get to observe that field in some locations, and we want to figure out what the value of the field was at an unobserved location. So what we need to solve is this problem. So we get a function from a Gaussian process. We get to observe it at some locations. So this x1, x2, xn would be the location you get to observe. And then we want to know what was the value of f at some unobserved location. So this is a mathematical statement of this problem of interpolating from sparse data into a regular grid. This x stars would be your regular grid locations. These are the observations, and you want to know, okay, given these observations, what do I know about the f at a grid point? So now again, to connect this with what we talked about on Monday, so remember we talked about estimation, prediction, and other things. So this is now an example of a prediction problem. It's an example of a prediction problem because remember this f is a random function, and especially this f at x star is a random variable. We're trying to guess what is the value of y star. That y star is random, so that task of guessing what is the value of y star is called a prediction problem. So this is exactly the same setting we had on Monday when we talked about prediction. So this is nice because we already now know how to do prediction. So specifically, okay, so the setting here is that, so since this f is a Gaussian process, it means that these observed values of f as well as the unobserved value of f, if you put them together into a big vector, they come from a multivariate normal because this is the defining feature of a Gaussian process. We can divide the mean vector into kind of the mean of the unobserved location and the mean of the observed locations. And then similarly, we can divide the covariance matrix into sort of the part that comes from the unobserved location, the observed locations, and then the cross covariance between the unobserved and observed locations. So now the question is that, okay, so given these elements, how do we predict this y star? And we know that answer from Monday, because we know what you do is that you ask, okay, what is the conditional distribution of y star given what I have observed? And since these both were, these together were multivariate Gaussian, and what we discussed about multivariate Gaussians tells us that this conditional distribution is also a Gaussian. In this case, it's a univariate Gaussian because this was univariate, and it has this form. And where did this come from? Well, it's just simply this equation using the notation we just defined. It's again not like super important. All right, so yeah, so this equation just came from what we knew about conditioning under multivariate Gaussians, and so it's not like again super important what the exact form here is. The key point is that this can be written down using these elements we just defined here, which ultimately depend on. That's what this all depends on at the end. It depends on what is your covariance function and what is your mean function. Okay, so now we have this conditional distribution. So this distribution tells us everything we know about the unobserved location given what we have observed. And notice to get this, the only thing we need to know about is how to work with multivariate Gaussian. So this is the reason Gaussian process is so popular, is that really the only thing you really need to know is how to work with multivariate Gaussians. So now that we have this, now we know from Monday that immediately we know how to make an optimal prediction. The optimal prediction is simply the conditional mean. So this was the result I highlighted on Monday. The optimal prediction is the conditional mean. Well, we can read off from here what the conditional mean is. It's simply the mean of this Gaussian here. So the optimal prediction is this. And then we can also find the predictive variance. So that's the conditional variance. It's this statement. And then how can we use this? Well, we talked on Monday about prediction intervals, and still we had an example of a Gaussian prediction interval. So now we can from this get a Gaussian prediction. Well, these two pieces give us the Gaussian prediction interval. It's this thing. So basically your optimal prediction, and then plus minus a certain number of times your conditional standard deviation. So this is basically exactly the same result we had on Monday. So this slide is basically exactly what we had on Monday, with slightly different notation, and also like adding the mean function in there, the mean vector in there. So just to summarize, so these two things, these two equations are worth highlighting a little bit. So this is now telling us, so from this formalism, we know that our best prediction of an unobserved location in a Gaussian process is this thing. And then the uncertainty of that prediction is this thing in the form of an interval. So I told you that this Gaussian process formalism gives you sort of the standard interpolants used in oceanography, and that's exactly what we have in here. So if you've ever heard of like interpolation of spatial data, you might have heard about treating if you're from statistics. You might have heard of objective mapping if you're from oceanography, or optimal interpolation if you're from atmospheric science. So those are all different names for exactly this thing in here. So this is the objective mapping prediction of an unknown or of unobserved location. So you have here, let's ignore the mean for a second. It's not, the mean is not super important. You have your data, then you have your data covariance matrix. You kind of decorrelate the observed data with the data covariance, and then you hit it with the data to grid covariance. And that gives you the optimally interpolated value. This is how, if you have taken like an oceanographic course on this, this may be how this has been explained to you. But now you see how to arrive at this from the perspective of Gaussian processes. And now the important thing to notice is that, of course, we don't just want one location. We usually want this over many locations, because what we want to do is to get this onto a regular grid. So we have like basically each location on a grid is a new location where we want to make a new prediction. Now, and the good news is that we can just basically repeat what we just saw. We just do it for each location you care about. So you just do that. You just compute this exact same thing over all the different locations you care about until you have infilled your whole grid. And in fact, you can take it a little bit further. You can also go through that same formalism for a whole vector of unobserved locations. So if you go through the same derivation we just did, in this case where, so that we just did here, we had a situation where we had a single unobserved location and then these were observed. But you can do exactly the same for a case where you have a whole bunch of unobserved locations and then the observed locations. And ask what is the conditional distribution of this thing in here, given these. And you arrive at equations that look very similar to this, except that there's like a matrix here and vector here. Like it really looks very, very similar. So the key point is that you can do also an optimal prediction into a vector of locations at once, and that has the benefit that it not only gives you a predictive kind of pointwise variance, but it also gives you the predictive covariances as well, which is captured in the covariance matrix in that predictive distribution of these unobserved locations. So, and the key point here, again, to emphasize is that the reason this is all tractable is the fact that it's a bit the basic definition of a Gaussian process, that finite evaluation of a Gaussian process are from a multivariate Gaussian, and that's the only thing they're using. All of this just flows directly from the fact that your finite evaluations are multivariate Gaussians and you work with the multivariate Gaussian. Okay, so now let's look at this in practice. So here's a concrete example. So this would be the case of a 1D X. Remember, it doesn't need to be 1D. I'll do a 2D example in a second, but here's a 1D example. So here's an X. So we have a random function over this X. So the random function would be this black line here. So this is we think of this black line as being a realization from a Gaussian process, a random function from a Gaussian process. And indeed, as was pointed out, this is a strongly correlated process over X. That's because of the covariance function there. And then now we say that, okay, we get to observe this function, this random function here, and there we have the circle. So that's the data we have. We have observed it at the circle locations. So that's the data we have, and now our task is to predict the value of this function at all the other locations. In practice, you do it over a fine grid, but when it's fine enough, you will not see that it's a grid. And then you do this over a fine grid, and then you ask, okay, like, what's my best prediction here, what's my best prediction here, and so forth. If you do that, you trace out the red curve. So the red curve is simply computed by doing this thing, but just on a very fine grid of locations, one location at a time. And then you can ask what is the uncertainty on that using the prediction interval, and that's the blue box. So now you can see that this is how you would do the interpolation and the answering quantification on the interpolation. You can see it's doing exactly what you would expect it to be doing. So at the locations you have observed, there's no observational error in this model right now. So at the observed locations, it will interpolate the data. It goes through excite the data. And then the real task is, okay, well, what do I know about the value of this function between the observations? How do I infill this gap? So you can see it's predicting something that looks pretty similar to the unobserved function. It's of course not perfect because we don't know what the truth is, but it's the optimal guess. And then you can also see it gives you a reasonable answering quantification. The answers are smaller near where you have observed, and the answers are bigger when you are far away from what you have observed. So this is what you get out of a Gaussian process. So okay, but now so here is a sort of not such a nice feature of this is the fact that this is forced to go through the data, because usually you don't want your interpolants to, or your spatio-temporal predictions to go through the data, because we know the data is noisy. Like in any real-world sensor, the data is noisy. So that would mean that you don't want it to go exactly through the data. You want it to go maybe near the data, not to the noise of the data. Okay. So how do you do that? So you change the model a little bit to do that. So to get around this thing of forcing the interpolation to go through the data, we need to add a bit of noise to the model. So we change the model. So instead of just saying that our yi is directly from the Gaussian process, we say it's from the Gaussian process plus a little bit of noise. And we are going to assume this noise is also Gaussian, so that everything is sort of in the Gaussian world, and nice. And then we assume this noise is independent from the Gaussian process. When we do that, this is called Gaussian process regression. And what is the practical effect of this is going to be that now it's not forced to go through those observations anymore, as I will show you in a second. Now, so this extra term here has a funny name. It's called the nugget effect. It's called like this because these techniques originally came from mining, where they were trying to find gold in soil. And so these would be like the nuggets of gold. This is capturing the nugget of gold that is there every once in a while. That's why it's called the nugget. All right. But in practice, especially in an earth science context, this epsilon in practice corresponds to either measurement error, like a sensor error, unexplained variation in your model, so all the variation that is not explained by the Gaussian process, or microscale variations. Especially in an oceanographic context, this will be the sub-mesoscale stuff, like all the stuff that your sensor doesn't resolve. It would go to this nugget. You need to capture all of that stuff, and then this is like all the sort of the resolved variation. All right. So now there's a choice to make. So in this case, there's two things you might want to predict. You might want to predict the value of f at an observed location, or the value of f plus the noise. The practical difference is that so in the first case, you just kind of go through the same formulas that we just did, and you find that the conditional distribution of this f star is this. It basically is the same equation as before, but there's this extra term here. You can do that, or you can ask what is the conditional distribution of this y star. And the only way they differ is that they have exactly the same mean, but the variance of the y star prediction is going to have an extra component from this nugget effect. So if you predict this, you're going to have a slightly bigger uncertainty prediction than in this case, but the mean prediction, the optimal prediction is going to be the same. And what does this look like in practice? So this would be what happens in our previous example. If we now add a little bit of measurement noise to these observations. So now you see they don't directly come from our function, they come from the function with a little bit of noise. So now you can see that first of all, the optimal prediction is not forced to go through the points anymore. It still kind of follows them, but it doesn't exactly go through the points. And then maybe more importantly, the uncertainty, if we compare the uncertainty here with 0 at the observed locations, now the uncertainty is not 0. It's still reduced at near the observed locations, but it's not 0 because there is the fact, it's accounting for the fact that we don't actually know what the extreme value was because there was little difference. So this is how it changes. And in fact, there's also another reason we like to do this. It makes the numerical computations much more stable. So this is actually super unstable numerically, and this is much more stable numerically. So there's also added benefits from doing this. Okay, so this was a 1D example. Now I want to show you what this looks like over a space. Okay, so what does this look like over a spatial domain? So here's a realization from a certain Gaussian process. So it's a random realization over, think of this as longitude and latitude. So think of like this could be like, I don't know, ocean temperature field or some other oceanographic field. And the idea is, okay, so this was a random realization. This is the underlying truth, the underlying physical truth. And then I suppose that I have observed it here, here, and here, where I have the black dots. So let's imagine I put like an Argo flow here, an Argo flow here, an Argo flow there. They got to observe that field at those locations. And then you go ahead and ask, what is my optimal prediction of the underlying field? So in other words, you ask what is the conditional mean of the underlying field, like point by point. And this gives you that. This is the optimal prediction. Then you can ask what is the answer of that prediction. So what is the conditional variance? This is the conditional variance. And then you can also you can also simulate from the conditional distribution. This is what we call a conditional simulation. This is the conditional simulation. So okay, so what do we have here? So this is the underlying truth. We have observed that these black dots. This is our best prediction. So you can see this would be the map. So now you can see it's kind of it was blue here, so it's kind of blue there. It was red here, so it's kind of red there. But you can see it's that the signal to noise ratio was not huge in this case. It's kind of smoothing out. The resolution of this map is not great because actually this was very sparse observation and compared to the variation. But this is the best prediction you get. This is the optimal prediction. You cannot do better in terms of a mean squared error. So the first thing you should realize here is that this doesn't look at all like the truth. It's the best prediction. This is the best you can do, but it doesn't look at all like the truth. So there's a sort of a high-level truth here, which is your best predictions are basically always smoothed out version of the truth. So any best prediction is always smoother than the truth, and this is actually true if you have sparse observations. So don't think of your maps as looking like the truth. They don't look like the truth. They look like the smoothed truth. That's very evident here. But you can also see. So then you can ask, okay. But here's my prediction. What is the answer on this prediction? So the answer is characterized. The pointwise answer is characterized by this plot here. What you can see here is that it kind of makes sense, right? So there I have observed the answer is small, and there I have not observed the answer is large. In fact, if I go very far from the observations, it's as if I did not observe anything. And this was a Gaussian process whose marginal variance was 1. So the variance is 1 here because effectively the data doesn't constrain the process here at all. So it's as if I had not observed the data at all. So this would give you the pointwise uncertainty on this prediction. So this tells you that, okay, like for example, if I want to know what is the uncertainty here, I will look here and say, okay, the answer is this. But there's a bit more to this because the thing is that so in this case this uncertainty only characterizes the pointwise uncertainty. It doesn't tell you anything about the dependence in the uncertainties, and that's actually important because this one way to understand this is that in this kind of a situation the uncertainties are also dependent. The uncertainties are correlated. And that correlation is characterized by the covariance matrix. So there is actually so in addition to this variance, there's a covariance matrix that would basically tell me that given the data how maybe in this one, given the data, how dependent is, for example, this location with this location? How dependent is this location with this location? So that information would be the covariance matrix. Now, the covariance matrix, even for a small domain like this, is a huge matrix. Something like I think it's like 1,500 by 1,500 in this case. You can imagine that if you have anything larger than this, that's a matrix you can't really work with. So it's not very practical to work with those conditional covariance matrices. So then how do you kind of account for these dependencies in those uncertainties given the data? Well, how do you account for the dependence in the uncertainties of your mapped fields? So the approach that we have been advocating, and Donata will also bring this up, is to look at these conditional simulations. So what is this? So given these observations, this whole domain has some big multivariate Gaussian distribution. So it's basically the case here. So yeah, if you ask what is the distribution of this whole collection of grid points, that is going to be some Gaussian with some mean and some covariance. And if you then ask what does a random simulation from this Gaussian look like, you get something like this. So this is a single realization from the conditional distribution of my map given the data. Okay. And then you can do this many times. At the very end, I have an example of doing this for Argo many times. You can then see that these conditional simulation ensembles, they give you like an ensemble representation of what are plausible realities given the observation we have. So this is a one possible reality, one possible guess of what this true field was given the data we have. And then you do this, of course, we don't know which what it was, so you do it many times. All of those would be like possible guesses of what the true field might look like. And you see, this looks very much more like the truth. So these simulations will look like the truth. They are actually supposed to look like the truth. So if you want something like that looks like a plausible truth, you need to look at these simulations instead of the mapped field. And it's very hard that, of course, this is so if you did this many times, this is the mean of those simulations, and if you did this many times, this is the variance of those simulations. And if that mean is still the best possible guess, like each of these is not a good guess on its own. The optimal best guess is this. Like if you want to get like a visual representation of what are the possible versions of the truth, you need to look at these. So now what we'll talk about is, so you realize that in order to do this is actually the previous comment. So in order to do this stuff, you need an idea of your mean function, your covariance function, and then those typically are some parametric families. So they have some parameters. You need to know about their parameters. Let's see how we're doing with time. Yeah, let's see how the time goes. But maybe so this part is maybe the most textbook part. So let's do so. I'll highlight the most important stuff here, and you'll have the slides to look at the details here later, because otherwise we will go too much to the coffee break. Because I want to get the last section of like what I can do to Argo data. So in this section I'll be brief, but you'll have the slides. Okay, so now in order to do all of this stuff we just discussed, you need a mean function, you need a covariance function. So the question is how do we get those? And actually this is a big focus of the field of spatial statistics, is much about how do you actually pick the covariance functions. So the first thing to notice is that it's not always so clear what part of the variation in your data should be in the mean function, what should be in the covariance function. This is actually true if you're in a case where you only get to see a single f. Like, imagine that the only thing I had was this black curve. What is the mean of this black curve? Like, I don't know, from a single curve, I don't know what the mean was. So especially if you're in a situation where you only get a single realization from a Gaussian process, there is an ambiguity in terms of what should be in the M and what should be in the covariance function. The default rule is that one person's mean structure is another person's covariance structure. So that's a non-trivial question. This is actually true if you do things like use this Gaussian process for things like surrogate models, where you really have just one f that you're trying to somehow have a Gaussian process representation for. It's not that obvious how to pick this. If you read some of the literature, some people say that you just set the mean to be 0, and that's it. That's not true. That's not actually true. So the predictions are affected by the mean. This is something that we will also bring up with Jonathan when we talk about the Argo data. So in the case of ocean data, the mean is your climatology. And what happens is that, so what happens is that if you have no data, if you have big gaps in the data, the best you can kind of predict with is this mean. So the predictions will revert to the mean in the absence of data. So yes, it matters very much what you pick as your mean, and especially in an ocean context, this mean is your climatology. If you have a big gap in your data, it will revert to the climatology, and it doesn't matter how you pick that climatology. Okay, but in practice what we do is that we have some parametric families for both the mean and the covariance. So I'll show you briefly some potential choices for those. So for the mean, we want the mean to be sort of flexible enough to capture the true mean structure, but not to be too flexible, so it doesn't start capturing any of the kind of randomness in the data that should be in the covariance. So some possible choices are some kind of a linear regression model, something called splines, or some nonlinear functions. Sometimes you use neural nets or other machine learning models. So those are all possible choices. I'll show you in the very end like what we use for the ARCO data. So these are the easy part. So let's move on. So more interesting and important part is how do you pick the covariance function. So the question is, the covariance function again is the covariance between the Gaussian process at two locations. So the question is, what function do we use? And remember, not all functions count, so they need to be positive, definite functions. So the first thing we often do is to assume that this function is what we call a stationary function. So what this means is that we often assume that this covariance between location x1 and x2 only depends on the separation of the locations. It doesn't depend on where they are exactly, it only depends on the separation. So in an Earth science context, it doesn't depend where in the planet you are, it only depends on how far your 2 points are. So that's the stationary guess answer. Sometimes we make this stronger and say that also the direction doesn't matter, in which case we call it an isotropic covariance, which means that it's a function of the norm between the separation of the two locations. Or we can make this a bit more general, which is this is usually what is actually a good model for Earth science data, is to kind of have this kind of a sort of a stretched and potentially rotated norm. So this is what is called geometric anisotropy. So this has the effect that you can basically have different dependencies in like latitude and longitude, and maybe oriented not along the axis, but with some kind of an orientation. All right. So if you focus on this case of geometric anisotropy, which is usually the most important for Earth science data, now there's two things we need to choose. So we need to pick this A, which is this matrix here, and then we need to pick the K, so this function here. So how do we pick those two? So the A, it's going to characterize the length scales of our dependence. In oceanographic context, these are called decorrelation scales. And someone already mentioned decorrelation scales. So they're going to be in this A. I'll show you a version of this in a second. And potential and orientation of the dependence, if you have non-diagonal elements, let's say. So that's sort of easy. The more important question is, what is this function f? So this function f, so if this controls the length scale of the dependence and the orientation of the dependence, this controls all the rest of the random field. Things like smoothness of the field, periodicity, and so forth. So there's a whole host of different choices of this scale. Like this is really like the bread and butter of spatio-temporal statistics, is to come up with like different versions of this scale. So here's a partial list. So you can have an exponential function. You can have a squared exponential function. This is something that's called the Gaussian kernel, but it's not really Gaussian because it's not a PDF. It just looks like a Gaussian PDF. But then really maybe the thing to remember is this Mathieu family. So this looks ugly and it's not very important what's in here. But this is a family of covariance functions that is often a good choice for physical science data. So this kind of a particle choice has a lot of nice properties. So the first nice property is that there is this parameter nu, which is called the smoothness parameter, that controls how smooth or rough these random fields are. And specifically, it controls how many times differentiable they are. So if you make this K nu larger, you will get more differentiable fields than for small nu. It also contains these two cases, special cases. So the particle choice of 1/2 for nu gives you the exponential. If you take nu to infinity, it gives you the Gaussian. So it's actually nice because this family contains these two things inside of this family. And then you often see, if you see this Mathieu covariance being used, you often see things like mu 1/2, 3/2, 5/2, and so forth. The reason for this is that in those cases, this weird Bessel function here goes away, and you get something that looks polynomial. It's kind of nice to work with. I think there's a question. Maybe let's take a brief. All right. So okay. So I promised a version of this A. So the easiest version of this A is if it's just a diagonal matrix. In which case, in this norm, this expression simplifies in such a way that it looks like this. So now you have a covariance function, which in some sense, like at least for me, is like the default choice if I try to work with spatial data or like Gaussian process more generally, is a covariance function that looks like this. So this will be a exponential covariance with different length scales, different decorrelation scales across your different input variables. So one of these could be longitude, one of them could be latitude, one of them could be time, or even some other setting. If you have some other features, your regression, these could be other input variables, and this would be controlling the length scales and such. So this is one possible choice, and this is often a good choice. So just to illustrate what those length scales mean, or the decorrelation scales, as is often the term used in oceanographic. So this is the case where sort of you have small values for those. So the dependence length scale is short. So you see that this process kind of varies across pretty small scales. Here you have the same, but for large length scales or large decorrelation scales. So it decorrelates less quickly. So you see that the patterns are larger, or the spatial dependence extends over a longer range than in this case. So this is the difference between large and small. And then these show like what happens if you have different scales across different axes. So here you will have a longer decorrelation scale on the x-axis and smaller on the y-axis. So you see the patterns are larger in this direction and smaller in this direction. And this is the opposite, the larger in this direction and smaller in this direction. So this is the anisotropic part of the model. And open oceanographic data has longer scales in this direction than in the north side direction. So this is relevant for ocean. Okay, so in all of those models, for example here, this model has parameters, there's phi, theta, and so forth. So still, even once you have picked this, you need to still estimate those parameters. In other words, you have unknown decorrelation scales, and this is the variance of the process, and you still don't know those. So whenever in statistics you have something you don't know, especially an unknown parameter, what you do, you try to estimate it. So this is the first part of Monday's lecture. We talked about parametric models. This is in this case, the Gaussian process, a parametric model where the parameters are these. And the question is, how do you estimate those? Well, you do exactly what we talked about on Monday, which is to do maximum likelihood. So you write down the likelihood function of this of your observations. But the observations from Gaussian process are just a multivariate Gaussian. So it's actually just a multivariate Gaussian likelihood. It's a likelihood function in those parameters of your covariance function. This is the nugget variance in this case, and then the potential parameter of your mean function. And then you go ahead and maximize this, as we discussed on Monday. We discussed on Monday why this is often a good choice. And this gives you now estimates of these parameters. And by the way, so until a few years ago, in oceanographic context, it was apparently not clear that this can be done. It was not clear that decorrelation scales can be estimated from the data. So this is something we pointed out in some work a few years ago. And since then I've become promoting the idea that yes, you can estimate these scales from the data. This is in fact very standard in statistics to estimate these parameters from the data. Of course, if you have very sparse data, then you will not get very good estimates. But if you have dense enough data, you can estimate this, and then you can basically get a data-driven Gaussian process model, and then use that to do the interpolation problem. Okay. So now we sort of know the base of Gaussian processes, and we know how to build these models. So now we'll put them together and see how to do this for ocean data. Hopefully that's a bit better. Okay, so now we have just learned the basics of working with Gaussian processes, including building those models. Now we'll put those together and see how to do this for ocean data. So all of this now boils down to, let's write down a Gaussian process model for our ocean data. So think of the Argo data or some other institute data. So we need now to write down a statistical model. And by the way, any model should start from this. This was Shane also emphasized this. Any model should start by writing down a statistical model. Once you have written down a statistical model, then you ask this model, then you start to interrogate the model. So we need a model first. So here's the model that we have been using in our work with ARCO data, and which I think is a pretty reasonable model for ocean data. So basically you say that I have here are my observations. So here, first of all, what are the indices? So the index I would be years, and J would be different indices, observations within a year. The first one is like, putting the year 1, year 2, and so forth data, and then these are the different points within a year. Then we say this comes from a random function. So this y is the value of a random function. So this is your oceanographic field at some location in longitude, latitude, and time. So a field over space and time. This is the location. This is where you got that data in space and time. It was observed in year I, so this would be the field at year I. And then there's some nugget effect, which in an oceanographic context would either include the sensor noise, or it would include both the sensor noise and then microscale structure. So all the kind of unresolved variation would also be there. And now, so since we do this with Gaussian processes, we assume that this F is from a Gaussian process with some mean and covariance. And then this, we assume this is also Gaussian here to be tested. So here's a Gaussian process model for ocean data. And what is this model saying? This model is saying that the observation, so this is basically saying that the year-to-year variations in my oceanographic field they are independent and identically distributed samples from a Gaussian process. So basically, there's an underlying Gaussian process that is characterizing the ocean variability. The different fields at different years, we assume those to be independent and replicates from the same underlying Gaussian process. So there's some underlying Gaussian process that is generating the different year-to-year versions of my field, and then we have a bit of noise in them. That's what this model is saying. So in this context, the parameters of this Gaussian process have a meaning. So this mean, so this M, this is the mean field or the mean function. So this is called climatology in this context. So it's the long-run average of my oceanographic fields. As you probably all know, this is called a climatology. So this M is your climatology, and then the variations around your climatology, those have a name. They're called anomalies. So in this language, this would be kind of the mean centered curve. You have the actual field minus the climatology. That difference is called an anomaly. In this language, you can just think of this as a mean-centered Gaussian process. You then have a model where you remove the mean, you have a Gaussian process with mean 0. And that Gaussian, now you can see what the Gaussian process is doing. The Gaussian process is reflecting the anomalies, the anomalous variations around the climatological mean. And that Gaussian process still depends on the covariance function. So the covariance function characterizes the spatio-temporal dependence in those anomalies. So this is nice because you can actually see this parameter, this Gaussian process that we just talked about, the things you need to write down a model for. You have a physical interpolation of those. The M is the climatology and the K is the covariance function of the anomalies. So now I'll show you the particle choices that we have been using with Jonathan and Tia, and which will be also used in the afternoon activity. So you first need a mean function. So this is the mean function we have been using. This origin comes from the Remick and Gilson climatology, if you're familiar with any of the other climatologies. So they use something like this. So you have basically I changed the notation here. The X is now my longitude, Y is latitude, T is time. So this is basically saying that my mean field, I can basically represent this as a second order polynomial of longitude, latitude, longitude and latitude. Then I have these sines and cosines here to reflect the seasonal cycle. This would basically make, these are seasonal harmonics. This part would capture the seasonal cycle. And then this is an addition we have made with Jonathan and Tia. So this is your climatology now. So this is adding a long-term time trend. So what this is doing is adding a climate change trend to the climatology. So here we are adding either a linear or quadratic time trend, a long-term trend into the climatology. And this becomes important. You will explore this in the afternoon activity. Also, Jonathan will talk about this after the break. What the effect of this adding this is. So we will see what effect it has to either have this in there or not have this in there. And this has to do with the fact that, as I mentioned, if you have no data, your maps will, your optimal predictions will revert to the mean field. They will revert to the climatology. So it matters what this is, or if this is in there or not in the case of sparse data. All right, that's the mean field. Then for the covariance, so this is easy because we already kind of talked about this. So a good choice for physical fields is often the matter covariance. So this would be like your default choice. Like, if you have a default choice for a point estimator, this is the MLE. The default choice for a covariance function is the matter. So you often start with the matter, and if you're not happy with the matter, then you try something else, but you first try the matter. So we want to have a spatio-temporal covariance function. We will have that as the matter, and then we have been using the geometric anisotropy that we talked about. So in this case, the inputs to this covariance function, or the process more generally, are longitude, latitude, and time. So you will have three components here in your anisotropic covariance. There is the longitude component, latitude component, and then the time component. Each of this is it's anisotropic in each of those dimensions. So there's a different decoration scale across each of those dimensions. So these decoration scales are unknown parameters of this covariance function that you would fit using the ML. In the fields you will see this afternoon, we use the exponential covariance. This is fine as long as you don't need a differentiable field. If you need a differentiable field, then as we discussed, you need a higher order smoothness for the matter. So something like a 3 would give you a differentiable field. Okay, so what I just said here, so here's a mean function, here's a covariance function, and by the way, this is stationary covariance because it's only a function of the difference. So this is all fine and good in a local situation. So this model is probably a pretty good model if you only have a small domain. But now there's a problem that really what you want to do this is over a global scale, or at least over some kind of a bigger scale than local. So this will probably be a terrible model in that case. And why is this a terrible model? Well, it's that kind of a second order polynomial in lateral longitude it's not going to capture the global climate risk. That's for sure. And also the stationarity assumption is very much questionable over anything than a regional scale. Like any oceanographic process, the variance is going to be very different depending on whether you're in an eddy-rich region versus a region with kind of a Coleman-White structure. The dependence length scales are going to be different depending on if you're near the equator or far away from the equator and so forth. So these assumptions are very much suspect for anything larger than a small scale. So to get around this, there's actually a very easy fix. The difficult fix is to come up with more complicated versions of this or more complicated version of this. That's the difficult fix. The easy fix is to still acknowledge that, well, this is probably a good model locally. If I take a small local window, this is probably a good model over a small local window. So the approach that we've used very successfully with many oceanographic variables that comes from this paper that I published a couple of years ago is using the idea that we fit these models locally. We use these models locally to interpolate in a local using kind of a local information, and then you have this kind of a moving window approach to Gaussian process regression. So basically, you have these local moving windows that are centered around the grid points where you want to do your interpolation. You fit the model locally using the data in the neighborhood of your grid point. So this is going to give you a locally stationary version of the model that is relevant for the local neighborhood. It's going to be terrible for the global structure, but it's fine for the local structure. And then you use that to interpolate. So this helps both with the modeling because it will capture the global non-stationary using these local models, but it also helps with the computations very much because you only work with small subsets of the data and you can parallelize that across the different windows. Okay, so now the rest, I'll just show you what this looks like. The rest is just pretty pictures to show you that this works. So here's some examples. So we are fitting these local GP models. So at each grid point, if you look at this very carefully, there are small grid points, 1 by 1 degree grid points. In each grid point, we put a local window. We estimate the parameters of the Gaussian process in the local window using the MLE. So this is showing, for example, what the estimated total variance of that field is. So you can recognize a lot of structure here. For example, high variance in the less than boundary currents, and smaller variance where you don't have that much variation going on. And we have similar things for the decoration scales and the other parameters. And also, by the way, I should say, this figure is produced by TIA. So this is thanks to TIA's great work. We have these estimates. So this is all joint work with TIA and Renata. That's important to point out. So okay, so this is the estimate parameters, one parameter. And then once we have the parameters, we can then just do their optimal predictions, do the kriging or the optimal interpolation. So here are some of those maps we get. So I'm showing just the anomalies. So these are the mean standard processes. So this is for ocean heat content. We've done this for many other variables, but this is for the ocean heat content, which you will see also this afternoon in the other stuff. So these are different monthly anomalies for Argo-based ocean heat content over a certain vertical section in the ocean. By the way, one thing I forgot to mention, let me just go back here because I promised John I will mention this. So in the afternoon, you will also explore what happens if these are not there, but you will also explore what happens if this time term is not there. So you will see like how these fields are different if you do interpolation only over space or if you do spatio-temporal interpolation. So this is one thing you will explore in the afternoon. But these are the versions with the spatio-temporal interpolation. And since you're an oceanographer, you recognize there's actually a lot of physics going on. So these are not just noise. There's a lot of, and Donata will actually convince you that these are not just noise. There's a lot of real interpolations that you get here. And then just the final thing I want to show you is the connection to this conditional simulation business, which you will also see this afternoon. So these are the optimal predictions. And as I told you, don't think of these as looking like the real fields. These are smooth versions of the real fields. So to understand what the real fields might look like, you might want to look at the conditional simulations. So here's a vertical conditional mean. So this is your best prediction. This is in a vertical data sparse part of the Argo record. So this is the best prediction. This is the optimally interpolated map of the ocean heat content anomaly. Here is a conditional simulation around that. So this is what the actual ocean might have looked like under our model. So here's one realization. This is one plausible version of the underlying truth. Here's the second one. Here's the second one. So these are all realizations from that high-dimensional multivariate Gaussian that is the underlying model for these oceanographic fields. And these are plausible realizations given the constraints from the data. They have as their mean this, and then the variance of these would reflect the pointwise answering. And then most importantly, these have also dependence. So these are these would reflect the dependence. And this now points to what Amy talked about on Monday, which is that if you do anything like, for example, an area average or any kind of a sum of this field, which is what we want because we want to get the global ocean heat content, which is the sum across this whole field. The sum depends not only on the variance but also the covariance. And these capture that covariance. Especially what you can simply do is that you take each of these realizations, you sum up the realization, you do it for each realization, you get a different sum for each realization. The spread of those realizations of the sum will reflect the uncertainty in that sum, including the correlations. And that's how you can get answers some things like the globally integrated ocean heat content. So this would be our latest estimate of the Argo-based ocean heat content over certain vertical section. The black curve is the optimal prediction, and the gray line is, you can see super well here. These are the different conditional simulations of the underlying truth. So given the constraint of the data, that's the ensemble spread of what the possible real values or real time series might have looked like. And then you do this many times and look at the spread, and now you get these uncertainty intervals. We had some discussion if these are prediction intervals or confidence intervals, but it's just called uncertainty intervals around those predictions from those conditional simulations. And this is what you will do in the afternoon. And now that brings us to the end. So the very last slide is some references if you want to read more about this. I'll maybe just point out the last one. So this handbook on spatial studies is a super good reference to learn more about this and to go much beyond what I talked about. So I very much highly recommend you have this in your library. And I will finish here and maybe we save questions maybe for the break. Yeah. Thank you very much.